Okay, so I'll talk about a library that we developed in IBM Research called HeLayers. You can see the names of the team that develops it, most of them. I'll start with a few words about homomorphic encryption and HeLayers, and then I'll spend most of the talk describing a new data structure and language for handling packing. And then I'll explain how we use it to run AI models under encryption. So homomorphic encryption allows clients to encrypt sensitive data on a trusted environment, send it to an untrusted environment like a server, and because of the special property of homomorphic encryption, the server can manipulate the data, for example, compute neural network inference, and return the encrypted result back to the client where it can be decrypted. Now, in common HE schemes, the ciphertext does not encrypt a single number, but a vector of numbers. In this example, it's 8 numbers. And every time we do an operation, it's performed element-wise on the ciphertext. So the output ciphertext here, in each slot, it contains the product of the two corresponding slots in the input. And in real-life scenarios, the ciphertext can be much bigger. It can be 8,000 numbers or 16,000 numbers or more. And packing means how we arrange the data that we want to work with inside all these slots in a way that utilize this best. This is called single instruction multiple data, or SIMD for short. So packing is how to arrange data inside the ciphertext that utilizes this SIMD feature in the best way. So a few words about HeLayers. We are using homomorphic encryption libraries. You see the names here, C, Latigo, etc. They provide us the basic primitive homomorphic operators, and we built on top of that additional layers of functionality. So the first layer, the abstraction layer, is providing a unified API to all of them. So you can write homomorphic encryption code without committing to a specific library. You can switch between them. The next layer defines a data structure called the tile tensor, which is responsible for the packing, which will be what I speak about now. So what's a tile tensor? Or actually, first, what's a tensor? So a tensor is a multi-dimensional array of numbers. It can be a vector, or a matrix, or a 3-dimensional array, or more. In this example, it's a matrix, a 5x6 matrix. And we want to pack it and encrypt it. And let's say again that the ciphertext size is 8 slots, same as before. And the idea of a tile tensor is that we don't think of a ciphertext necessarily as a flat vector. We think of it itself as a small tensor. In this example, we think of it as a tensor of 2x4, a matrix of 2x4, which is again 8 slots. And we call it a tile because we combine several of these until we have enough space to store the matrix that we want. So you can see how the matrix is stored here. It's basically divided into contiguous blocks of 2x4. There's some extra space, so the extra space is padded with 0. And that's a tile tensor, a tensor broken into tiles. And we have this language here, we call it a tile tensor shape, that specifies what we did. So the two numbers above the line specifies the shape of the original tensor we started with, in this case, 5x6. And the two numbers below the line indicate the shape of the tile, 2x4. And by choosing different tile shapes, we can choose different kinds of packing. So here, for example, we chose 4x2. We got this one, this packing. This is 2x4 again, and 1x8, which basically means to pack the matrix row by row. So as you can see, each arrangement here arranges different numbers in the ciphertext. And you can easily switch between the option. You can easily choose an option by simply specifying a tile shape. Here's another option I want to mention. I won't mention all options, but here's another one. This is a row vector. We can pack it as before. So again, you can see the vector here. The extra space is padded with zeros. Another option is to put this asterisk here, which means we want to use this dimension in a different way. Instead of not really using it, we use it for duplication. So each value will be duplicated over and over again along this dimension. In this example, it means that the vector will be duplicated twice, once in each row. And why is it useful? Let me show you an example. Say we want to multiply a matrix by a vector. So the way we can do it with style tensors, we'll pack the matrix in the same way we saw before. And the vector will treat it as a row vector and pack it again in the same way I just showed you with this duplicated dimension. And now I don't have time to get into all the details, so I'll run over it quickly. What we do is we multiply element-wise these two tile tensors. So first we broadcast the smaller one to have the same size as the bigger one, which basically means to duplicate this row of tiles. Then we can do the element-wise multiplication, which multiplies the vector with each row of our matrix. And then we sum over the second dimension, which produces the correct result. So you can see why the duplication was useful. It allowed us to be able to duplicate the tiles so that the vector will be multiplied with each row. So this language, it covers a lot. It covers a lot of options. Let me show you a few examples. These are two papers that discuss, among other things, they discuss packing options. And like many other papers, they define new terminology, describe the packing techniques using lengthy text and figures. And with this tile tensor shape language, we can define each of these packing techniques in a single line. And also, usually, we can define the way that it's being operated on using basic operators on tensors. So if the community will adopt this language, it will be easier to communicate. And also, of course, using tile tensor, it's easier to implement it. It does all the packing algorithms for you, and you can easily switch between different packing options. So tile tensors cover a lot of known packing techniques. They also offer some new ones. Let me show you an example. This is a square 6x6 matrix. And say we want to do an operation called rolling, which basically means to take that top green row here and move it to the bottom. With the previous packing that I showed you, it would be costly to perform. But here's a new packing. So we call it interleaved packing. It is marked by this tilde here. So this means that the first dimension is going to be not the ordinary packing, but the interleaved packing. And this is how it looks like. So let me explain what's the difference. Let's look at the first column of our original matrix. It's 0, 10, 20, 30, 40, 50. And in the tile tensor, you can see the numbers are not contiguously placed. What we do is every time we move to the next number, we also move to the next tile. So it's 0, 10, 20. Now we're back to the beginning, 30, 40, 50. This is how they are arranged. And with this arrangement, it's easy to do a roll operation. Here's how it's done. What we do is we take the first row of tiles and move them to the bottom, and also roll each of these tiles. So we roll only these two tiles. And now I'll read the numbers again in the interleaved order. So it's 10, 20, 30, 40, 50, 0, exactly matching the column order of the rolled matrix. So the tile tensor now represents the rolled matrix, which is what we wanted. And using roll operations, we can define convolution. So if we have an ordinary matrix I, by rolling it with various offsets and scaling and summing, this is equivalent to convolution. And part of the idea of tile tensors is that once we define a computation using operators on tensors, we can take these operators as is and move them to tile tensor, and we get the same results. So tile tensor and tensor support the same operators with the same meaning. So we can compute convolution this way. And again, it's efficient because we only did homomorphic operations only on 2 tiles out of 6. Okay, so on to the next layer, the AI layer. It is used for running AI models. What it does, it can read an AI model from Onyx file or other formats that we support, and it reads from them a tensor circuit, a circuit that defines a computation on tensors with various operators. So the first step that it does, it converts all the tensors to tile tensors. So this is easy because, as I just explained, running the same operators on tile tensor will produce the same result. So this circuit has the same meaning. The hard part is to find the tile tensor shape, the best tile tensor shapes. So for some choices, there might be some pre-processing nodes that need to be inserted in between. Some choices, there's no need to be pre-processing in between. So this is one of the considerations that the automatic optimization process that we have considers. So it to automatically tune the tile tensor shapes to achieve the best latency that we can get, or we can configure it to achieve other goals, best memory, or whatever we tune it to achieve. I'll skip this slide. So here's a few performance results. In the paper, we reported AlexNet. Since then, we continued to the bigger network, ResNet. You can see 4 variants of ResNet here. We report how we did it here in this new publication here. And I want to emphasize 2 points, or 3 points. One is that our tool is general purpose. It has no specific optimization for a specific architecture. It can run any Onyx file and optimize for it. We can run arbitrarily large and arbitrarily complex circuits. And for small one, we can reach much better performance. We can reach even milliseconds. And also for big networks, we expect improvement soon. Okay, so summary. We recommend using tile tensors and tile tensor shapes. We have a homepage where you can read more about HeLayers and all the updates. It's also the artifact in the paper. HeLayers has Python and C++ APIs. It's very easy to install for Python. You just write pip install PyHeLayers, and you'll get all of that. And thank you.
Thank you so much. So we already have the first question that came in. Do you need to design different shape of tiles for different computing platforms, for example, GPU or CPU, specifically for faster computation?
Yes, yes. When we do the optimization, we consider the specific timing it takes on a specific hardware, and we get different results. If it's CPU or GPU or different architectures, definitely yes.
Okay, thank you. So for now, there are no more questions on Zulip, so a quick question from me. So in case when the tensor could fully fit into the size of the ciphertext, does it still make sense to use tiling? And if yes, then how and why?
Yes, it does. So a lot of paper present techniques that are equivalent to tiling. They don't use the word tiling, but they use equivalent techniques for various reasons. So there are many reasons to do that. I want to mention one reason that is not mentioned in other papers, is that that it's common that that if you have a certain tensor, then you select a ciphertext big enough to hold it. But using these techniques, you can eliminate this consideration. You can choose a ciphertext based on whatever size that fits best from security or performance consideration. You don't need to care about the size of your data. So it works better this way.
Yeah, that's a big advantage. Thank you. So no more questions on Zulip for now. A quick question from me. Are there any planned extensions to your library that you're working on currently?
Yes, we already have multi-key support. We plan to extend it for better multi-key support, improved optimization, reducing key sizes, and many other plans.
Quite a lot. Good luck. Okay, thank you so much.
Thank you.
Let's thank the speaker again.
Thank you.